Well, today we're going to start talking about the organic compounds and the branch of chemistry that is called organic chemistry, which studies specifically organic compounds that are composed mostly of carbon. So organic compound is a compound made from carbon and hydrogen atoms first and foremost. It may contain other atoms of other nonmetals such as oxygen, halogens like chloride, bromide, iodide, sulfur, nitrogen, phosphorus. Some pretty specific organic compounds may even contain the atoms of metals, but we're not going to talk about those. It just goes way too complicated. Organic compounds are all around us, and you can find them in the gas, various drugs, cosmetics, plastics, and perfumes. So the formulas of organic compounds are usually written with the carbons being first, and then hydrogens, and then any other elements. Usually organic compounds contain covalent bonds. Most of the bonds are nonpolar or weakly polar. Organic compounds usually have low boiling and melting points. Many of them are flammable and easily undergo combustion. And what's important, many organic compounds, but not all of them, are not soluble or poorly soluble in water, such as vegetable oil, which is a mixture of organic compounds. Contrary to organic compounds, inorganic compounds usually have high melting and boiling points, just like a table salt. Inorganic compounds that are not polar covalent but are ionic are usually soluble in water, and most of them cannot be burned in the air or oxygen. So for comparison, propane, which is a gas at the normal temperature, can be used as a fuel, which means it can be burned in oxygen. Sodium chloride, or table salt, is an ionic inorganic compound, which, as you know, cannot be burned in oxygen and has extremely high melting and boiling points. So this table summarizes some differences between organic and organic compounds. Elements that are present, they're different. Particles usually molecular, while in inorganic many of them are ionic. Bonding is covalent in organic, but ionic in inorganic. Bonds in organic compounds are usually nonpolar. Low melting and boiling points, high flammability, and lack of water solubility. The first type of organic compounds that we're going to talk about are hydrocarbons. These are organic compounds that contain only two types of atoms, carbon and hydrogen. The distinctive feature of carbon in organic compounds is that every carbon in organic compounds has 4 bonds. Here you can see carbon forming 4 bonds with 4 atoms of hydrogen. Hydrocarbons that contain only single bonds, whether those bonds are between carbons or between carbon and hydrogen, are called saturated hydrocarbons. Let's take a look at the methane, the simplest saturated hydrocarbon. In this molecule, carbon forms 4 covalent bonds. You can see electron dot formula on the left, expanded structural formula in the center, and ball and stick model on the right. You can notice that bond angles between the CH-CH bonds are 109 degrees, which makes the shape of the molecule tetrahedral. In ethane, which contains 2 carbons and 6 hydrogens, each tetrahedral carbon forms 3 covalent bonds with a hydrogen and 1 here at the center to the other carbon. So again, you can see the electron dot formula, the expanded structural formula, the ball and stick model. Now, why there are so many carbon compounds? Because the covalent bond between carbon atoms is very strong, and that means that you can form long chains of carbons, and that explains the variety and diversity of various organic compounds. So the first class of hydrocarbons that we're going to talk about are alkanes. Those are hydrocarbons that contain only single carbon-carbon and carbon-hydrogen bonds. They are formed by a continuous chain of carbon atoms. They have names that end in "ane." So the naming of alkanes, as the naming of all organic compounds goes, is following the rules set up by International Unit of Pure and Applied Chemistry System, or IUPAC. And usually, to numerate how many carbons are in the particular alkane, we use Greek prefixes, as you will see it pretty soon. So first four, kind of weird: methane, ethane, propane, and butane. But then you have pent, which is 5, pentane; hex, which is 6, hexane; hept, which is 7, heptane; oct, 8, non, 9, and dec, 10. Now, there are several ways to show the structure of an alkane. Instead of the full structural formula, sometimes we use a expanded structural formula. Sometimes we use a condensed structural formula, where each carbon atom and all the hydrogens that are attached to this atom, written as a group. The subscript next to the hydrogen indicates the number of hydrogen atoms that make bonds to each carbon atom. So for butane, for instance, with 4 carbons, this is the condensed structural formula. So this is an expanded, this is condensed. This is an expanded, this is condensed. Now, alkanes, of course, can be represented by the molecular formulas. For example, butane will be C4H10, or skeletal formulas. So this black line represents the skeletal formula. Each corner, or the end of that broken line, zigzag line, represents a carbon and all associated hydrogens. Now, it's important that carbon atoms, when they form a single carbon-carbon bond, they can rotate against each other. So you can see here in this formula for ethane, this group can rotate, okay? And that rotation leads to the different conformations of the organic molecule. So these individual groups rotate about the single carbon-carbon bond. They appear at different angles. So let's take a look at the representation of more complex alkanes, such as the hexane. So hexane, which contains 6 carbons, can be represented as the molecular formula. The ball and stick model, which of course nobody's drawing by themselves. An expanded structural formula, which takes a lot of time to draw. A condensed structural formula, either of those is fine, and as a skeletal formula. All of these representations are correct. So for butane, for instance, you can do an expanded structural formula, ball and stick. Look how many different condensed structural formulas you can draw, because, you know, the angles are not particularly fixed here, and then the skeletal formulas. Now, another group of alkanes are cycloalkanes. They form a cycle, and for instance, for cyclopropane, the normal propane will have a formula, the regular propane will be C3H8. But when they form a cycle, they lose 2 hydrogens. So now the formula for cyclopropane will be C3H6. So basically the difference in the name is that you put the prefix cyclo before the name of the alkane chain with the same number of carbons. So here you have cyclopropane with corresponding condensed and skeletal, cyclobutane, cyclopentane, and cyclohexane. Now, interestingly, when an alkane has more than 3 carbon atoms, so 4, 5, and so on and so forth, the atoms can be arranged so that one of the carbons can form a side group called a branch or a substituent. Okay, like here you have a butane, and you have another butane, but one of the carbons is now hanging off on the side as a substituent. So here, 2 structural isomers of butane, straight chain and the branch chain. These 2 molecules are called structural isomers because they have the same molecular formula, but the arrangement of atoms is different. So basically, same number of atoms is bonded in a different order. Now, generally speaking, substituents are atoms or groups of atoms that are binding to the carbon chain that can include alkyl or halo groups. Halo means halogens. Now, alkyl groups are groups of carbon atoms, of course with hydrogen, that are attached to carbon chain, and according to IUPAC system, they're named with the ending YL. Hala substituents are halogen atoms that are attached to carbon chain, and they are named as fluoro, chloro, bromo, or ido. So CH3 will be methyl. This CH3, CH2, ethyl. CH3, CH2, CH2, propyl. If same propyl is bound to a carbon chain via the middle carbon, it's isopropyl. And here you have fluoro, chloro, bromo, and iodine. Let's take a look at the naming. So what is the name of this compound? First, we need to identify the longest chain of carbon atoms. It's going to be this, 5, pentane. If we will try something else, this will be 4. This will be 4 as well. So it's going to be pentane. Now we need to number the carbon atoms, starting from the end that is closest to a substituent, but in this case, substituent is in the center, so it doesn't really matter. So 1, 2, 3, 4, 5. And now, oh, sorry, yeah. So closest substituent is chloride. Okay, so it's going to be at position 2, it's going to be chloro. Okay, so you end up with 2 chloro, 3 methyl pentane. So once again, you number in a way so that the first carbon happens to be at the end that is closest to any substituent. So using the same approach, you can name cycloalkanes. When there is only one substituent attached to a carbon, you just put the name of the substituent in front of the name of the cycloalkane, and you don't really need a number. So this will be ethyl cyclohexane. Now for haloalkanes, you just put substituents in the alphabetical order. So halo group should be numbered according to the carbon where it is attached to the alkane. So here we go. Chloromethane, bromoethane, 1,1-fluoropropane. Common names include methyl chloride, ethyl bromide, propyl fluoride. So just like we can name the alkane based on the formula, we can draw the formula based on the name. So for instance, we have a name 1-chloro 1,2-dimethyl-heptane. Heptane means that there are 7 carbons in the biggest chain. Methyl groups are located on carbons 1 and 2, and there's a chlorine on carbon 1. So let's take a look. Let's draw the condensed structural formula for 3-bromo-1-chlorobutane. So main chain will be butane, 4 carbons, and then we have 3 bromo and 1 chloro. So at the position 3, so chloro and bromo, at the position 3 there will be the bromine atom, and at position 1 there will be chlorine atom. So this is the condensed structural formula, this is the skeletal formula. Alkanes, for instance, used as a waxy coating in fruits and vegetables, to enhance the appearance and to help retain moisture. Now, alkanes with 1 to 4 carbons are gases at the room temperature, often used as a heating fuels. Alkanes with 5 to 8 carbons are very, very volatile liquids that also can be used as fuels. So they are easily evaporated. Alkanes with 9 to 17 carbons are liquids with fairly high boiling points, and you can find them in the liquids like kerosene, diesel, motor oil, jet fuels. And 18 or more carbon atom containing alkanes are usually solids, we call them paraffins. Now, for instance, petroleum jelly or Vaseline is the mixture of hydrocarbons, and most of them contain more than 25 carbon atoms. So alkanes, as you can figure, they are nonpolar, they are not soluble in water, they're lighter than water, flammable in the air, and basically crude oil to a large extent consists of alkanes. So if there is an oil spill in the ocean, the crude oil will float on the water because of all the light alkanes, which first of all cannot mix with water, and second, lighter than that, and that will result in formation of a thin layer of oil on the surface. Now, alkanes have a strong carbon-carbon bonds, which means that when they react with oxygen, first of all, they make carbon dioxide and water, but second, what's more important, they release a substantial amount of energy when carbon-carbon bonds are broken in the reaction of combustion. For instance, methane and propane are gases that are used to cook food on the stoves, to heat our homes. Butane, you can buy it in the store for camping trips. It is used in portable burners. Now, there are some hydrocarbons that contain not single but double or triple bonds between carbons. We call them alkenes and alkanes and alkenes respectively. So ethene here, often called acetylene, is widely used in welding. It actively reacts with oxygen and produces really, really high temperature flames with a temperature above 3300 Celsius. So these hydrocarbons, alkanes and alkenes, contain double and triple bonds, and they're called unsaturated hydrocarbons because they don't contain the maximum possible number of hydrogen atoms. So that means that they can react with hydrogen gas to saturate double and triple bonds, to increase the number of hydrogen atoms, and eventually become alkanes. So alkenes contain one or more carbon-carbon double bonds. Ethene, for instance, C2H4, 2 carbon atoms are connected by double bond. Each carbon in the double bond also is attached to 2 hydrogen atoms, and that means that each of these groups is a trigonal planar arrangement where angles between the bonds are 120 degrees. Ethene, or more commonly known as ethylene, helps plants to ripe, and actually some plants and produce is treated with ethylene to accelerate the ripening. It also accelerates the breakdown of cellulose in plants. That results flowers to wilt, leaves to fall from the trees, and so on and so forth. Alkenes contain triple bonds, one or more than one. For instance, ethene, 2 carbon atoms are connected by triple bond, and each carbon. So you have this, and then each carbon is also connected to a hydrogen bond. So here you have a typical linear arrangement where bonds have an angle of 180 degrees. Now what about IUPAC names? So similar names are similar to those of alkanes. Basically use an alkane name with the same number of carbon atoms, but you replace ane with ene for alkenes or YNE for alkenes. So ethane, ethane, ethene, propane, propane, propene. So let's try to name some of the unsaturated hydrocarbons. So here you have skeletal formulas for hydrocarbons, and first you need to identify the longest carbon chain. So here it will be 5, so pent-in, and here it's going to be 6, so hexane. The double bond is at the second carbon. You always number the carbon chain so that the end, starting with 1, is the closest to the double bond. So it's 2 pentene, and here it's 2 hexane. And then you put the location and the name of substituent, in the alphabetical order. So you go, if this is number 2 and 3, this is going to be number 4. So 4-methyl, 2-pentene. No substituents here, so just 2-hexane. Now cycloalkenes have a double bond within the ring. So you want to assign the numbers so that the double bond is between the carbon 1 and carbon 2. You don't need to include the numbers for the double bond if it's only 1. So in this case, you go 1 and 2, and then substituent should have the lowest number possible. So it's going to be 3-methyl cyclopentene. Now, the interesting feature of unsaturated hydrocarbons is that they have so-called cis and trans isomers. The groups of atoms attached to the carbons connected on the double bond, they can form different structures, resulting in geometric isomers. So let's take a look. So the double bond is rigid and cannot rotate, which kind of makes sense. If you take 2 carbons and connect them by 2 bonds, they won't rotate. So attached groups are held in the fixed positions. And that results in the formation of cis and trans isomers. So cis and trans isomers can form when 2 different groups are attached to the carbons connected by the double bond. So here you can see hydrogen and chloride, and here you can see hydrogen and chloride. But here you can see chloride on one side, and here you can see chlorides on the opposite sides. So essentially this is the cis isomer, cis because chlorides are on the same side, substituents are on the same side. And here you have trans isomer because substituents are on the opposite sides. Cis and trans isomers have different physical and different chemical properties. So this illustrates how cis isomers are different from trans isomers. So as we just discussed, in cis isomers, the groups, the substituent groups, in this case alkyl groups, are attached on the same side of the double bonds, and hydrogens are located on the other side. In the trans isomer, the groups, the substituent groups and hydrogens are on the opposite sides of the double bond. So when you name such geometric isomers of alkenes, for instance, you put the prefix of cis or trans in front of the alkene name. So this will be cis 1,2-dibromoethene, and this will be trans 1,2-dibromoethene. Now, we're going to discuss the properties of unsaturated hydrocarbons now, and the saturation of hydrocarbons plays an important role, for instance, in the food production, because hydrogenation of unsaturated oils is used to convert the double bonds in oils to make them into saturated fats, but we call them trans fats, like the fats that are found in margarine. So in alkenes and alkynes, the double and triple bonds are extremely reactive. So you can add hydrogen or water to the carbons in the double or triple bond. This bond can be easily broken, which provides electrons to form new bonds. For instance, in the reaction of hydrogenation, you can take alkene, add hydrogen molecule using catalyst, forming alkane. In the reaction of hydration, you can take alkene, add water, and using as a catalyst, using some strong acid, form an alcohol. So what does hydrogenation reaction look like? So here you have unsaturated ethene, and you add hydrogen to a double bond, or in case of ethine, two hydrogen molecules to triple bond. Using different catalysts, the result for both reactions will be the same. It's going to be ethane. So catalysts in this case are used to speed up the reaction. So when you add hydrogen to double bonds in vegetable oil, like this oleic acid, hydrogenation of oleic acid, results in the formation of stearic acid. And that results in the formation of compounds with higher melting points, which basically makes them solid at the room temperature. So you've got vegetable shortening, you've got margarine. The point is, you can use relatively cheap vegetable oil and convert it into kind of useful, solid, I can't believe it's not a butter. The downside of it is that this conversion results in the production of so-called trans fats, which are extremely harmful for your cardiovascular system. So in hydration reaction, alkene reacts with water, forming alcohol. So hydrogen will form a bond with a carbon that has more hydrogen atoms. And hydroxyl group from water will form a bond with a second carbon, which has fewer hydrogen atoms. The catalyst in this case will be strong acid, such as sulfuric acid. And here's an example. So this is the general idea of alkene plus water forms alcohol with OH group on the side. It's a functional group of all alcohols. If we take ethene, both carbons have same number of hydrogens, so really there is no difference, But let's take a look at the products of the addition of water to each of these alkenes. So how do we approach this? We need to figure out which carbon has more hydrogens. In this case, it's really easy to figure out. In this case, it's a little bit more complicated, but you can see that hydrogen will be added to the carbon which has fewer carbons attached to it. So another group of hydrocarbons are aromatic compounds, which were first isolated in 1825 by Michael Faraday. He isolated benzene, which is basically a 6-carbon ring with alternating double bonds. And molecular formula for benzene is C6H6. So benzene is called aromatic compound. Why aromatic? Well, actually, benzene smells pretty bad, but many derivatives of benzene actually have a decent smell, and they were discovered before that, and this is why they're called now aromatic compounds. So here in the benzene, you have 6 carbons organized in a ring, and each carbon is bonded to a single hydrogen. So you can see that there are alternating double bonds. But the thing is, you can put double bonds anywhere you want. So at the end of the day, the electrons, the free electrons that are present on carbons, electrons that form those supposed double bonds, are actually equally shared by all carbons. So this is why we represent benzene with a circle in the center. So you can see that circle in the center represents the equal sharing of electrons between all the carbon atoms. So benzene derivatives are aromatic compounds that contain a benzene ring and a single substituent. Since it's only one substituent, we don't need to number the ring. Many of those substituents have common names. For instance, methylbenzene is known as toluene. Aminobenzene is known as aniline. It's a very strong dye. And hydroxybenzene is known as phenol, which at some point was used as the disinfectant and antiseptic agent. So when you have more than one substituent, so 2, 3, and so on and so forth, you number the benzene ring so that the numbers of the substituents are the lowest. So this is chlorobenzene. This is 1, 2, not 3, 4, not 5, 6, 1, 2 dichlorobenzene. This is 1, 3 dichlorobenzene. Hypothetically, it can be 1, 2, 3, 4, 5, 1, 5, but no, it's 1, 3. And in this case, it's 1, 4. There's no other option. Sometimes you can use a common name. In this case, the carbon atom that is attached to the sort of name-giving substituent, like amino group in bromoaniline, or hydroxyl group in phenol, or methyl group in toluene, gives the number 1 to the corresponding carbon. So this is number 1, 3 bromoaniline. This is number 1, 2, 4 bromo, 2 chlorophenol. This is number 1, 2, 4, 2, 6 bromo, 4 chlorotoluene. So let's take a look at the names for each of these compounds. So this is chlorobenzene, of course. This is 1, 3 dimethyl benzene. So this is kind of a concept map for the organic compounds. So study it, and that's going to be a part of your next exam.